Welcome to this session on radio wave propagation in urban areas, in cities where we have buildings, streets, cars, vehicles, trees, obstacles, posts, and many other things. So the modeling of this environment is not easy, it is difficult. To model this environment, we have two paths or two tracks to do so. We have the theoretical models, we have theoretical models, and also we have empirical models. And we have empirical models. Theoretical models are based on equations, and in order to model all details of the city, equations and boundary conditions would be very difficult. Because of that, theoretical models involve many simplifications, which make them not very suitable in some situations for urban propagation. On the other hand, empirical models are based on actual measurements in the environment, which would be more realistic, but it applies only to the same environment. For other environments, we use correction factors. The communication in cities, or the personal communications in general services, are available within this frequency band from 30 megahertz to 3000 gigahertz. This is called the very high frequency bands and ultra high frequency band. Very high frequency band and ultra high frequency band. The signal strength near the mobile varies significantly. Now we start here with the theoretical models. There is this as an example. We have this the diffracting screens model. We have this model. Okay. The diffracting screens model. Okay. We have the diffracting screens model. The figure here summarizes the model. The model assumes same height of buildings, which is not realistic, of course. Also assumes the same spacing or separation between buildings. And here the base station is higher than the buildings. There is another equation also or the same equation also can be modified to be valid for the base station lower than the buildings. As you can see, the wave may come here and diffract from this edge of building and go directly into the mobile telephone or receiver, or it can, the diffraction here can reach the next building and reflected towards the mobile or receiver. Also, it can be diffracted from any building edge here to reach the mobile by some way or another. Here diffraction, then ground reflection, then diffraction, and so on. The building height is denoted by B. The base station height is denoted by HB, and D is the distance between the base station and the last building before the mobile telephone, and S is the distance between buildings where the mobile is. The mobile height is denoted by HM, and the distance between the building before the mobile and the mobile itself is called W in this model. This is the scenario when the base station, this is base station here base station here, as you can see, this is the base station, and this is the antenna, transmitting antenna, and here the base station height is lower than the building's heights. So the wave will be diffracted until it will be creeping above the rooftops until it will reach, diffracted here and reach directly the telephone, or reflected from the wall of the building after the telephone. Again, here we have the height of the mobile is denoted by HM, and the separation between buildings, between the last building and the building before the mobile, is denoted by S, and W is the distance between the last building before the mobile and the mobile itself. The average path loss, propagation loss, is given by this equation: minus F minus LE1 minus LE2 minus 18 log 17 HB plus D squared over 17 HB. This factor is a correction for the earth curvature, this factor. Now F is the free space loss, we already know that. This is 32.4 plus 20 log the frequency in megahertz and the distance in kilometers. This is the free space loss. In addition to the free space loss, we have the diffraction component due to last building edge before the mobile. Diffraction component due to the last building here before the mobile. And it is given by this equation, minus 10 log. Now let's clarify. The HB, as we said, is the height of the mobile station, and D is the distance here. D is the distance between the base station and the building before the last building before the mobile. Okay, now here also we have this equation, LE1 minus 10 log GM as function of theta. Theta is this is theta, this is the horizontal, and this is the last building before the mobile, and this is the ray towards the mobile, this is theta. And GM, as we said, is the mobile telephone gain, the gain of the mobile telephone. K is the propagation constant. I mean, GM is the antenna gain of the mobile telephone, and B is the building height here. HM is the mobile height, and W is this distance, the last building before the mobile and the mobile itself. This actually W, and theta is given by this. This is theta, as you can see. This is theta. So theta is equal tan inverse of this, see, of this distance here, of this distance. This is B minus HM over this distance here, which is W, as you can see, and S is this distance between the buildings. LE2 in this equation is equal to, is given by this formula, minus 10 log GB the gain of the base station antenna times the QEL squared. QE, we use QE when the base station antenna is higher than the building, and we use QL, as you see, when the base station is lower than the building. So how can we determine when the base station height is greater than B, is the building height, plus root lambda S. S is the separation between buildings, as you can see, and lambda is the wavelength. If this equation applies, we use QE. If this equation applies, we use QL. Now QL and QE are given by these equations. S is the separation between the buildings, B is the building height, HB is the base station height, and S separation between buildings. This is, as we B is the building height and HB is the antenna height of the base station, and S the separation between buildings, and so on. QE is given by this equation, where the same here, lambda is the wavelength and S is the separation between buildings, as you can see here. This is S. Okay. Note that D in these equations is inserted in kilometers, and LDS is given, the result will be in dB, and base station height in meter, mobile height in meters, and building height in meters, separation between buildings in meters. The distance between the last building before the mobile and the mobile is W in meters also. D, the distance between the mobile and the building before the base station, is in kilometer, because this is a long distance, is usually a long distance. This is this distance. This is D, and also D for the this also. This is in measured in kilometers. And the frequency in megahertz. Now note that in QE here, if the distance is large, 1000 time distance is large as compared with the base station height, which is usually the case, the argument here is very small. And we know from math that the argument, tan inverse of an argument, tan of theta is equal theta when theta is very small in radian. So we replace, you see, tan inverse of HB over 1000 B is replaced by the argument itself, by the angle, because the angle is very small. It's HB over 1000. Now consider HB over D only, or consider HD only. This is 1 over HD, of course, because here we have multiplied by 1. This is 1 over HD. So 1 over D raised to the power of 0.9, because here D is here. So the field is proportional, because Q squared is power and QE is proportional to field. So the electric field is proportional to 1 over D to the power 0.9. It's here times 1, you can see. So it is 1 over D all to the power 0.9. This is point, which is equal 1 over D to the power 0.9. Okay, as here. In addition to the free space dependence of 1 over D, we multiply and this, and we will obtain 1 over D to the power 1 plus 0.9 is 1.9. This is the electric field proportional to this quantity. The power is the squared proportional to the squared of the electric field, the square of the electric field, or electric field squared. And when we square this, we multiply the exponent by 2, it will be 3.8. So the field decays very fast. These equations are not valid close to the radio horizon, which is defined by this equation, dt equal twice AE HAE is the equivalent radius of the Earth, which was for standard atmospheric conditions 8,497 kilometers. The actual radius of the Earth, of course, is what was 6,378 kilometers. And H here is the base station height minus the building height. Beyond horizon, the losses are greatly greater than predicted by this model. This is explanation of the radio horizon dt given by this equation. We already explained that. And AE is 8497 kilometer, the effective earth radius. H is the antenna height here, and B is the building height. The COAST 231 model, it was created by the European Research Committee, and the fraction over knife edge obstacles, we already explained that in an earlier session. We move now to the empirical models for urban propagation, and we will stop here. Thank you for listening. If you have any comments or questions, please let me know.